Hello, Jeremy.
Hello.
Christian, I see you're on the online today.
Yes. Yep. Sorry, just a second. Yes, I have my PowerPoint though. I figured I could just share my screen after class if you wanted to do it that way.
Yes, I'll go to my office and then we'll connect from there.
Okay.
Oh, Gordon. Okay. We had a homework that was due today, and I just half an hour ago or so I posted a new homework. Make this due next Monday. And midterm 2 is on 26th. The final exam is in the first week of May, so typically it is about the second week, so be aware of that. So right after April finishes, so semester also finishes. Okay. And the final exam dates are out, but I haven't yet brought it out. Look into it. So I'll do that soon. Okay. And I haven't graded the midterm yet. I was almost beginning to do that today, but I will do that very quickly, and you should have your grades there at least this quarter of the grades, maybe 1/3 of the semester grades. I think that's the way to put it. Okay, so okay.
you manage to grade my homework?
No, I haven't. Yeah, all that is together. Yeah, just because it's on the email, it just stays there. Yeah, yeah, but I do want to get rid of it because it occupies my email, and I like that. So yeah, there are a few great homework that yeah, I haven't got to.
Right.
Yeah. But yeah, I think every other day, but expect it soon. So we haven't yet completed on what we wanted to do. We wanted to get the magnetic field for a circular current carrying wire. We said we will try to get an exact expression for that. But for that, we need to introduce a new set of functions because the integrals that comes across comes for that purpose is not are not doable. So let's take a small digression here. These are called elliptic integrals. But before that, let's think of an ellipse. And ask what is the circumference of an ellipse? That should be a straightforward thing to ask. Like circle has the circumference as, what is the circumference of a circle? Of given radius A, let's say R. No? Circumference, what's the area of a circle? Let's begin with that.
Area is pi r squared, right?
Area is pi r square. Yes, a circle, let's begin with the circle, right? So circle area is, so this is a simple circle, right? It has only one parameter, A, and area is pi times r square, a square, right? Pi a square. What about the perimeter or the length, the circumference, right? Good, so that's 2 pi a. So there's only one parameter that describes the area and circle, and that's 2 pi a and pi a square. And the equation of a circle in rectangular coordinates is x square plus y square is equal to a square. The equation of a circle. And what's the equation of a circle in polar coordinates? Like polar coordinates is, instead of x and y, we say this is r, right? So this is, that's your x, that's your y. Instead we say this is r and this is angle theta. Right? In terms of r and theta, what's the equation of a circle?
R cosine theta plus r sine theta is the radius, or I guess square maybe.
So cosine theta plus sine theta, no? Cover again?
R, yeah, right. R times cosine theta plus sine theta.
Is equal to radius?
The radius, right?
No. That's wrong. Is that right? No, I don't think so.
One.
Oh, squared, right? You have to square the whole.
Yeah. Gordon, you said something?
I thought it was equal. I guess.
Oh, you put cosine square. Yeah, but okay, no. But yeah, go along this line. So cosine square plus sine square theta is equal to 1.
Yeah.
So r square is equal to a square. So r equal to a, that's it. So equation of a circle in polar coordinate is just r equal to a. No condition on theta. For every theta, if you fix, you say the radius E is equal to a constant, that's the rate. So equation of the circle is very straightforward and in polar coordinates, correct? Okay, that's all. Circle. You know that reasonably well. We want to talk about an ellipse, and an ellipse is described as a squeezed circle, but it's not squeezed any squeezed circle. It has the equation, that's your x and that's your y. Let's say this is length A and that's length B. That's half. Half. A and B. And the equation of an ellipse satisfies in rectangular coordinates x squared plus a squared plus y squared over b squared is equal to 1. If A was equal to B, then of course it becomes a circle. And so a few things come up, right? What is all this in for an ellipse? What is the area of an ellipse? What is the circumference of an ellipse? And what's the equation of an ellipse in polar coordinates? In polar coordinates. Okay. All that is your quiz. Okay. Here, let's concentrate on the circumference. By the way, have you ever come across what is the circumference of an ellipse? Any guesses? Look it up and tell me. Since you guys have computers or phones with you, just look up what is the circumference of an ellipse. And
Pi times square root of 2 times the half of a squared plus half of b squared.
no, that's not correct.
That's what this thing is.
So it does not have an expression in terms of simple functions. Circumference of an ellipse does not have a closed form expression in terms of simple functions that we have studied. It doesn't exist. But of course, there is an ellipse formula you will find, but that is what we are going to study today. Okay, so we're going to see what the circumference of an ellipse is, but it cannot be expressed in terms of simple functions. By simple functions, I mean exponential, sine, cosine. Like, how many functions have you guys studied? Like, how many functions can you guys think of? Let's put all the polynomial functions into one group. Like anything that can be written in terms of x squared, x cubed, or fractions of that. If you put them all as single structure, then the new ones that we usually give it a name is exponential, log, and the sine and cosine, pretty much. of course, you can do so much out of this that it's plenty. But these are most of the simple functions are, and that's what we mean by the elementary functions that we are aware of. And circumference of an ellipse cannot be expressed in terms of that. So what do we mean by that? So let's try to actually calculate that. So how will you calculate the ellipse? Try to calculate the circumference of an ellipse using calculus, let's say. How do you go about doing that? So that's one quadrant. So surely since in the symmetric, if we know the length of this, we know the length of 4 times that will be the length of that, right? So this is your x, and that's your y. Let's have y as a function of x. You can solve for that. Y as a function of x is equal to b times square root of 1 minus b square, no, x square over b square, no, x square over a square. Correct? And so that's okay. So I know this function value now. Given a function, how do you calculate the length of that curve that the function goes around? How do you go about doing that? What will be the strategy? So the strategy typically is, so let's say, for example, this could have been a circle, right? So you would say the perimeter, let's call this the perimeter P, right? So this is the perimeter of this particular curve. So since I know that I'm talking about the ellipse, perimeter of an ellipse, so let me say this is 4 times the integral. So integral of what? I want to talk about a line element, so that's my line element. That's not straight, that's neither vertical, neither horizontal, but in very infinitely small element, let's call that ds. If I add up all those elements from x equal to 0 to x equal to a, I get my circumference, right? That will be the simple definition of the circumference. Now the question is, what is that length? ds. Right? That's the question. But ds, we know, that's a length of that's a distance between 2 objects that are really close to each other, and they are connected by this function y of x. So we say, what is ds in a plane? That's equal to dx square plus dy square. That's how we measure distances. Make a small distance dx, that's a small distance dy. Think of it, this is your dx, that's your dy, and that's your ds, right? So that's connected by the right triangle property, right? So this is not really horizontal. This could be having a triangle, that could be having a slope. Usually when we think of a rectangular coordinate system, we are good with integrating over x or y. Integrating over ds is harder, right? So we would like to convert it into dx. For that, we notice that ds would be equal to square root of this, and I also take a dx out. So 1 plus. That's an important step there, because that tells us that ds is related to dx in terms of derivative of the function, which makes sense because the length of this tiny element, it also depends on how much it is inclined, right? The slope should decide that, and the slope indeed is deciding that length. Right? So that's a calculus concept, and from that point on, we just have to put this in and calculate. Right? From that point on, it's just algebraic or calculus. So x is equal to 0, x is equal to a, ds is dx times square root of 1 plus, what is dy by dx? So that's dy by dx square. Actually, there should be a new quiz, right? So do this for a circle also, like I'm doing this for an ellipse. If you, instead of y of x being this function, y of x for a circle, you should get the circumference of a circle, correct? So that should be straightforward, and just what you have to do is, instead of b, you just have to say this is equal to a. Right? That's the only difference that will come back. So the two quiz problems are the area of an ellipse, circumference of an ellipse, equation of an ellipse in polar coordinates, everything about an ellipse, but you should have seen these things before. Okay, so to be able to do this integral, we should have an expression for the derivative, but we can find the derivative, right? That's dy by dx can be calculated. That's just the square root of a function. I take the derivative with respect to x, so that's b times 1 over 2. This is square root when you do. That whole function is raised to half, subtracted from 1 from half, so that takes it to the denominator. So that's the derivative there, but then we also have to take the derivative of the argument in there. Derivative of 1 is 0, and we have minus minus 2 times x over a square. So let's write that as minus b over a times x over a over 1 minus x squared over a square. Substitute this in here, and we have to evaluate that integral. That's 4 times 0 to a dx. You have to square this quantity, so that's 1 plus b squared over a squared, x squared over a squared. And the denominator, I have 1 minus x squared a squared. Let's make the denominator the same. Let's put it on the other side. And what I have is so the perimeter of this ellipse is equal to 4 times integral of the variable x going from 0 to a, and this is 1 plus, I have to pull this on the, when it goes to the numerator, I can collect the pieces of x squared minus, or x squared, let's say. So that's can be written in this form, or this is minus, so minus, and this is 1 minus x squared minus x squared. Ellipse seems to be characterized by 2 parameters, a and b, but there is a property of an ellipse that's called the eccentricity. And eccentricity is how squeezed the ellipse is. If if a circle is an extreme version of that, if b is equal to a, then the eccentricity is considered to be 0. And if you stretch it too much, then the maximum it can go is 1. So eccentricity is defined as 1 minus b square over a square and the square root of that. Right? That's defined as the eccentricity of an ellipse. So if b is equal to a, which is a circle, e is equal to 0. And as b goes to 0, e approaches 1. So as you choose our b to be small and small, then e approaches 1. In that form, this is equal to 4 times 0 to a x. So this is 1 minus e square times x square over 1 minus, oh, there was an x square over a square in the numerator, right? So this was x square over a square. This integral cannot be done. That's a catch. That's why you cannot find the ellipse perimeter of an ellipse. But let's at least write this in a slightly nicer manner, right? So let's substitute x over a is equal to, let's say, psi, right? So let's substitute. Yeah, let's substitute x over a is equal to sine of psi, let's say. So dx is equal to a times cosine hyperbolic of psi times d psi. And how does this integral change? It is 4. When x is equal to a, that's equal to 1. The left hand side substitution is 1. Sine of the variable psi is equal to 1. That's sine of what quantity is, no, sorry, when x is equal to 0, this is 0. So sine of what is equal to 0? So that's psi is equal to 0. So that means this is psi equal to 0. When x is equal to a, this becomes 1. So that means psi is equal to pi by 2. Dx is a times cosine of psi d psi. In the numerator, you get 1 minus e square. X over a is sine square psi. And in the denominator, we get 1 minus sine square. But 1 minus sine square psi is nothing but cosine square psi. Right? So there's a small cancellation there. So cosine psi cancels exactly this quantity. And a comes out, so I can write this integral as, is this still in the board? So this is 4 times a times 0 to pi by 2. This is an integral. The denominator is 1, so we could actually at least write it in a slightly better form. Doesn't matter because anyway it is not doable, so it doesn't matter what is better or not. But that's an integral you cannot do, right? It cannot be expressed, it cannot be completed in terms of the standard substitutions or anything, you know. So whenever you come across something that you cannot proceed, but either way, this does give a value, right? The circumference of a circle is indeed a number. So, and we do need this a lot. So we define a function. So we go ahead and define this to be equal to 4 times A times, this is dependent only on E, notice. Psi is just there to, it's a dummy variable, integral variable, it goes from 0 to pi by 2. Eventually it depends only on E, so we define this function as an elliptic integral, which is a function of E. So this E will be called, so let me define this. So E of, let's say in general it is defined as K, so that's 0 pi by 2 d psi 1 minus K squared sine square psi, and this is called the elliptic integral or complete elliptic integral. Of the first kind. Few points on the, few things about the name. Elliptic integral because it's, we were calculating the ellipse, right? I think that's why it's called an elliptic integral. First kind, we will very soon see a second kind also. Usually whenever you have a differential equation, there are two types of functions that always we will introduce whenever you see Bessel. As you proceed, you will see new functions around, and they will always come in pairs. Like exponential also, there is an exponentially decaying function and there is an exponentially growing function. So this is elliptic integral of first kind, and there is a second kind. One decays and one grows as k increases. Why is it called a complete? What do you mean by an, so there is something called an incomplete elliptic integral also. By incomplete, we mean we don't integrate all the way from 0 to pi by 2. You integrate from 0 to some finite value, and then that's called an incomplete elliptic integral. So as I said, this is a function, so we should be able to evaluate this for some values of the function, like in principle for any value. So let's see. So let's go back to the board space. So this is the elliptic integral of the first kind is equal to E of k times 0. Let's go back and see what is our perimeter of an ellipse. That came out to be 4 times A times the elliptic integral with respect to the eccentricity E, right? We already said that E is equal to 0 corresponds to a circle. And we know the answer for a circle. So let's try to calculate what is the elliptic integral for eccentricity equal to 0. So E is elliptic integral for k equal to 0. So how do we calculate it? We just substitute that in there, right? So that's 0 to pi by 2 d psi. K is equal to 0, so that's just 1 minus 0. But that's just 1. Integral of this is pi by 2. So we now know that the elliptic integral at the value 0, like sine of 0 is 0, so that this elliptic integral at k equal to 0 has a value of pi by 2, and perimeter then of a circle now is equal to 4a times pi by 2, and that's 2 pi a, which we know is correct. Right? So we have at least calculated one. it seems like there should be one more place we can actually calculate, right? What if k was equal to 1? When k is equal to 1, so that seems like E is equal to 1. What happens when E is equal to 1? That's another extreme scenario we get. When E is equal to 1, at least if you go into that curve that we had, this actually gets squeezed, right? This is your ellipse which has a length A, but B is going almost to 0. So the eccentricity is 1 minus 0 over A square, and that tends to 1. But what will be the circumference of such an ellipse? When you squeeze this really hard, it is length 2A, double it, so we expect it to be 4 times A, but let's see if we can get that or not. So P of when E is equal to 1, that's equal to 4 times A times the elliptic integral of 1. When k is equal to 1, so that's equal to, what is elliptic integral of 1? That is 0 to pi by 2 e psi 1 minus sine square psi. K is equal to 1, so this is, but that makes that simple because 1 minus sine square psi is cosine psi. You know how to do that. Psi, cosine psi, that's integral of sine, or the value is sine of psi evaluated between 0 and pi by 2. That's 1 minus 0, so that's equal to 1. So the value of this is 1, which indeed makes this perimeter to be exactly equal to 4 times A, which makes sense, right? So you go here, that's 1, then you come, that's 2 times A, that's 3 times A, and 4 times A. So it makes sense that its length should be 4A. So we got values of this integral for at least 2 points, 2 extreme points. So what can we, suppose we were to plot this as a function of k, and this is k is equal to 1, and that's k equal to 0. Somewhere when k is equal to 1, we have it to be exactly equal to 1. And when k is equal to 0, we have pi by 2. So if this is 1, so pi by 2 is 1.5 something. So that's pi by 2. And this is E of k we are trying to plot. So that's 1 point, and that's the other point. And the other point is not easy to calculate. If you want to calculate this function at any other point of k, whether it's negative, positive, anywhere else, it is not easy to calculate. And this, but if you were to numerically do this for each value, put it in and numerically evaluate this, this comes out to be exactly like this. So it's just decays down, and there is a small, it first decays slowly and then starts decaying faster and faster. If you want to keep going this side, it actually goes onto the left also, but typically it is defined for k less than 1 and greater than or equal to 0. But that doesn't mean that it is restricted to that. It is exactly like sine function. You generally extend this definitions to or continue this definitions to a larger domain of the independent variable. So that's our elliptic integral of the first kind, and we are introducing this because when we calculate the magnetic field of a current carrying wire, we are going to get an integral which is not doable, but then it is exactly this. So then we just have to write it in this form instead of trying to do the integral. Okay, so that's elliptic integral of the first kind, and then you say what is the elliptic integral of second kind, right? So complete elliptic integral of the second kind. And together, these two functions are like sine and cosines. If you have sine and cosine functions, you have what is called a Fourier transformation, and you can do a lot of things with that. Every function in principle can be written in terms of sine and cosine functions. Similarly, this forms a vector space, and elliptic integrals also can be used to describe general function. What is the elliptic integral of the second kind? This will be defined as K. This is slightly confusing because this is a capital K, especially when you write it on the board, like when I write it. Typographically, it is easier because capital and small k is distinguished. But here, this is a small k, and that's a capital K. That's a complete elliptic integral of the second kind. And that's equal to, that's defined as, very similar to the other one, except that this is in the denominator. This is d psi over 1 minus k squared. And it is good to at least point out, I won't be doing it here. Where do you come across complete elliptic integral of the second kind? And I can just, or before that, let me, before I spend some time on that, let me first evaluate what is k of 0. What is k of 0? Can you guys immediately tell me? Just substitute k equal to 0 and try to evaluate the integral. Pi over 2, very good. Right, so k is equal to 0, so that's just pi over 2, very good. And k equal to 1 is actually tricky. Okay, elliptic integral of the first kind came out nice. Here, this comes out to be 0 to pi by 2 psi times 1 minus sine squared psi. That's cosine psi. That's the area, like if you were to actually plot this psi, and then there is a cosine, 1 over cosine of psi, right? 1 over cosine of psi going from 0 to pi by 2. When cosine of psi is 0, when psi is 0, cosine of psi is 1, so it starts from 1. But when psi approaches pi by 2, it becomes 0 and it starts to blow up. Right? So this is pi by 2, 0 to pi by 2. So it quickly blows up. But that's okay. Just blowing up doesn't mean that the area should blow up. Like suppose a function grows to infinity like this, right? And the integral of that is this area, correct? What will that area be? Should it be infinity?
Can you zoom the or move the camera down a little bit, please?
Oh. Sorry. Oh, so for quite some time you guys didn't follow.
Yeah.
Okay. So the point is, I was saying k of 0, you evaluate this. That was, so when you put k equal to 0, it is just 0 to pi by 2. But when k is equal to 1, it is d psi by cosine of psi. And if I want to evaluate that, I have to evaluate this area, right? Cosine of psi is this function. When psi is equal to 0, it is 1. When psi is equal to pi by 2, it goes to infinity. It is a curve of this kind. And the area underneath that is the integral. Area underneath a function is the integral. So the question is, the question I'm asking is, if a function grows to infinity, can the area underneath that necessarily go to infinity, or can it be finite? Can that area be finite?
Yeah, and like direct delta function if it's shrunk down
That's
as
a
a
that's a reasonable uh, 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 example one is thinking. Yes, that's correct. A more like Dirac delta is good, but it's an extreme. It's hard to imagine that. But a more concrete function is exponential of x, right? If you were to have exponential function, this is e raised to minus x, correct? Is this now within the board? Let me just go to. Yeah. If you have exponential of x, what is the area underneath this? Equal to? Like, this goes all the way to infinity. Like I can turn this around and that's vertical. What's this area equal to? That's integral of exponential of minus x, correct? You can do it in your head maybe. Integral of exponential of minus x going from 0 to infinity.
minus e to the minus x.
So it is 0 to infinity. Yeah? This is 1 by the way.
Is it one?
This is 1. Yes. So integral, good. So this is 0 to infinity of dx e raised to minus x. So that whole area, in terms of this unit, if this was 1 meter, that area is 1 meter squared. Slightly non-trivial, right? Because you go, this is like simple 1 plus 1 by 2 plus 1 by 4 plus 1 by 8. You think it goes to infinity, but they are smaller and smaller, so they don't add up too much. But very good. So that's area is 1. Right? So similarly, so it shouldn't surprise that this area can be finite, but it can be finite, I said, right? It doesn't have to be not necessarily finite. Right? If this decays fast enough, then it is finite. But this is an example where this is not finite. Okay, even though I said I try to motivate that this could be finite. So this actually goes to infinity. This area is infinite. And then you try to plot this, right? The idea was to plot. So I want to plot k is equal to 0 and k equal to 1. And we already said there is a value 1 here. And there is pi by 2 here. That's your e of k. That's e of k. The elliptic integral of the first kind. Of the second kind also begins with pi over 2. But then I said it goes all the way to infinity at k equal to 1. So this actually blows up. It starts going to infinity. So that's the function. So if you want what is elliptic integral, that function, if you can draw that precisely enough, that's your elliptic integral of the second kind. That's a very dull function, right? Doesn't happen, like it just keeps growing. But then quadratic function is also monotonic. So this is your elliptic integral of the first and second kind. And we will write our expression for magnetic field in this using these expression. But I wanted to do one thing before. Oh yeah, I wanted to mention, where do you come across this elliptic integral of the second kind? First kind we said is at least one place where it comes about is circumference of the ellipse itself. The second kind shows up in the situation where you're doing a pendulum problem. If you have a pendulum, there is so let's say this is your rigid pendulum which is hanging, and let's say the time period that it takes to go around, how much is that equal to? Time period in what is that given by? Time period of pendulum in terms of length out? No? It is given in terms of 2 pi times L over G. Is that familiar? Is that familiar? So how much time it takes for one cycle, right? Start from here, go all the way there and come back. It depends on the length of the pendulum and on which planet you're, that's all. Right? If you're on, if you do this on Mars, it will behave differently than you're on Earth. But if you're on Earth, it seems like the length L is the only thing that decides it. What if I pull this pendulum all the way till here and then push it? So there are two pendulums I construct. So one is I do this here like this. And the second one is a small one. Is that clear? By this I mean the amplitude, right? Amplitude of the pendulum is how much you stretch this and leave. Here I have a small amplitude, here I have a large amplitude. Correct? Whose time period will be larger according to this formula? If both have the same length L. It seems like both the pendulums have the same time period. Is that correct?
If the length is the same, yeah.
If the length is the same according to this formula, it is. But then if you were to go back and look into this calculation, there was an assumption made in that calculation. Okay? And the assumption was that you won't make this amplitude too large. And now the question comes, what does it mean by large? Well, with respect to what? So what if you make it 60 degrees? How much error do you make in this? So this, the more an exact expression for K is, so the time period is, that is a elliptic integral times sine of, this is the amplitude of this argument of this is an angle. How much you pull this. Since notice this function, this actually, even though it looks like this, it actually goes all the way till here and then starts growing up. For a long time, it is actually pretty close to 1. So you don't make an error when angles are small. If you're within 60 degrees, you make about 10% error, 10% error. That's the amount of error you make. And 10% is good error. Good if you have such a huge simplification. You don't have to introduce elliptic integral. So that's a huge simplification. So 10% is good. But in principle, you can get it as precise as you want if you series expand. So where do you see elliptic integral of the second kind? That's in simple harmonic oscillator. That's a more correct version format. Okay, I'll stop here, and next time we'll start working on the current kind wire, or a little more actually. We want to no, actually, yeah, derivatives are not necessary. This is sufficient. That's all. Thank you.
Thank you. Should I just rejoin this conference or stay logged in, or?
I will actually log you out and then you log back in. How about that? So
Okay.
that I finish the recording here.
Okay.